All right, so yesterday we went over how to write the names for compounds with multivalent metals in them, and then just at the end of the day, I gave you this compound here and asked you what its name would be. Okay, and we were initially quite stumped over that. Okay, but then we realized that on the top left of our periodic table is the table of common polyatomic ions, which is where we can find things like this. Okay. Anytime you have a compound that contains a polyatomic ion, it is by default what kind of compound? If it has a polyatomic ion in it, it is ionic. Okay, it has to be. All right, so it will almost always start with a metal, and by almost always I mean 99.9% of the time. The one exception is if you have this polyatomic ion to start the compound. Okay, this is ammonium. It is the only positively charged polyatomic ion on your chart that you will deal with. So since it's positive, it behaves like a metal. Right? Even though it starts with nitrogen, it's actually metallic or behaves in a metallic way. All right, so once in a while you might run into a compound like this. Okay, this would be ammonium chloride. Okay, we name it the same as any other ionic compound. Okay, and this here would be sodium hydroxide. Okay, all right, what if I had this? Okay, what's Mg? It's magnesium. Okay, and what's NO3? Nitrate. This is just magnesium nitrate. Okay, it looks like it should be a lot more complex than that, but it's an ionic compound. The numbers don't affect the names. All right. Now the reason that we have brackets and a number outside of the brackets is because of the drop and swap. Okay, so if I'm looking at this compound in terms of a drop and swap, magnesium has a 2+ charge, nitrate has a -1 charge. Okay, so when I drop and swap, okay, the 1 would come over here, but we don't write ones, and the 2 comes over here, but I can't write it here. Right, because then it's 32 oxygens and 1 nitrogen, which is not the same as saying 2 nitrates. Everybody follow? So we have to enclose, if we're doing a drop and swap, which we haven't even talked about yet, okay, with a polyatomic ion, then you have to put a bracket around it if you have to put another number there. If it's just going to be a 1, like sodium hydroxide was, then we don't need it. Okay, but if you have to use another number with a swap and drop, then you enclose it in brackets. Okay? These are new things, I know, okay, but they're not hard things. All right, let's look at molecular compounds here. Okay, so molecular compounds are made up of 2 non-metals. Okay, and unlike their ionic counterparts, these bonds are very, very strong because the relationship between these 2 atoms is based on shared need. That is, they have to both have this electron or electrons that they are sharing. Okay, they can't trade them. It doesn't work for 2 nonmetals to trade electrons like a metal and a nonmetal do in an ionic compound. Right? So a covalent or molecular covalent bond is very, very strong. So if we're looking at water, which is what we see on the left here, okay, oxygen has 6 electrons in its outer shell, and hydrogen has 1. So when hydrogen and oxygen bond together, obviously you need 2 hydrogens to fill oxygen's outer shell with 8 electrons. Okay, but hydrogen needs to have 2, so they share them. Okay, the sharing's not equal. We'll talk about that when we talk about polar bonds, but okay, the sharing is there, and so as a result, these have to stay together very, very strongly. Okay, because they don't get to trade. Okay, if they're going to get their outer shell full, they have to stay together. Okay, everybody all right with that? All right, so molecular compounds arise, obviously, like we said, when 2 nonmetals react to form a new substance. All right, so they're made up of 2 nonmetals. Okay, and because nonmetals usually have negative charges, okay, no one element gets to keep the electrons. The electrons are shared, okay, in these type of bonds. Okay, when we name molecular compounds, things are a little bit different, right? We name them from left to right according to the formula. Okay, so whatever atom or element appears first, we name it first. Whatever element is second, we name it second. Okay, we change the ending of the second element to "ide," right? That still holds up, so it's still going to end in "ide," right? But now we have to use prefixes to tell people how many of everything there is, right? Because there's not necessarily a fixed ratio for molecular compounds to go together. Right? We already talked about how with ionic compounds, because they have to have a net charge of 0, there can only be this many of this and this many of that. It doesn't work that way with molecular compounds. They can make weird bonds and things like that where there can be different numbers of things and the compound can still work. Okay, so we have to use prefixes in a molecular compound to tell people how much of everything there is. Okay, so if we have this compound right here, okay, we have carbon, we have 2 sulfurs, so this is carbon disulfide. Okay. Why didn't I put a mono on the carbon? Hmm? Right. It's the first compound is the only one that doesn't get mono. Okay. So if you have one of the first thing, sorry, not compound, first element, okay, you never use mono on the first one. Every other prefix you do, okay, but for some reason not mono. I think that's because somewhere deep inside, chemists have this inferiority complex, so they must have really weird rules to make things difficult to make themselves feel better. Probably not, but that's what I tell people. Okay. All right. So for our next one, we've got 2 nitrogens and 1 oxygen. So we have dinitrogen and what did I make? What did I do wrong here? Right. It should be dinitrogen monoxide. Okay. You could write it 2 different ways. Okay. You could write it like this. Okay. You can write monoxide, or you can write mono hyphen oxide. Either one is fine, but nobody really pronounces it the other way. Okay, either one is fine to write though. Okay, and then obviously it goes even higher. So if we're needing the prefixes, you might want to write these down if you don't know the prefixes, to at least 10, okay, we need to know them. So mono is 1. You can write these on your periodic table, yes. Di is 2, okay, tri is 3, tetra is 4, okay, penta is 5, hexa is 6. Now, this is one, especially if you took French immersion, that you're going to have to change, because our chem guys do not like septa. Okay, like it drives Mr. Real insane when people use that. So we use hepta here. I don't really care one way or the other, but the chem guys don't like it. I'm a physics guy, so it doesn't bother me. Okay, hepta is 7. Okay, octa is 8. Nona is 9. And deca is 10. Shouldn't need anything beyond that. Okay, so at this time, it's also important to note that some elements can actually form molecular bonds with themselves. Okay, so if you see in this diagram here, they've got like a hydrogen molecule. That is 2 hydrogen atoms bonded together. Okay, same with oxygen, nitrogen, chlorine. There's actually a number of elements that do this. We call them the molecular elements because they actually don't occur in nature as a single atom. Okay, they always just bond with themselves. It does not change their name. Okay, we don't name the hydrogen molecule. We don't call that dihydrogen. Okay, it's just hydrogen. That's the only way it comes. Okay, same with oxygen, same with nitrogen. So on your periodic table, I've already color coded them. Right, the yellow ones are what we call the diatomic molecular elements. Nona, N-O-N-A. Okay, so the yellow ones are the diatomic molecular elements. That means they come as a pair. All right, so whenever they're in a reaction by themselves, okay, by themselves is the key here, okay, they are a 2, so O2, H2, N2, okay, Cl2, all the ones that are yellow, when they are by themselves as an element, are actually a molecule of 2 atoms. Okay, I also have 2 other ones color-coded on there. I've got phosphorus in purple. Phosphorus is a tetrad. That means it comes as a molecule made up of 4 phosphorus atoms. Okay, and sulfur is in there, and it's color coded in kind of like a peach. It was supposed to be orange, but it ended up kind of peach. Okay, it is a octet. That is, it comes as a molecule made of 8 sulfur atoms. Right, so those are important to remember. Okay, you can write that on your periodic table as well. Yellow equals diatomic. Okay, purple equals set of 4 or tetrad. Okay, orange or peach equals octet. You can do that if you want. Okay, questions on any of that so far? Okay, so there really aren't any new rules to do with molecular compounds. The rules are the same as what you learned in grade 9 because there's nothing really to add to it, okay? Because there's no like polyatomic ions or anything like that in molecular compounds, right? So everything should be the same as before. So I want you guys to try the first 4 here, okay? Write their names and then we'll go through them together and see how we did. Okay, so we'll go over these here in just a sec, but guys, it's super important. I know this is, again, kind of review for you, but being able to name compounds or write their formulas, which we haven't gone over yet, but will, is the most basic skill for high school chemistry. Okay, if you can't do that, then you won't be able to write chemical equations, and then you won't be able to balance them, and then you won't be able to do stoichiometry, and. Okay, you won't be able to do basically anything to do with high school chemistry if this basic fundamental skill is not at its best for you. Okay, so make sure that if you're having trouble with this or you have any questions, you got to come in and see me for help. Okay, ask for help. Okay, so we can make sure that this makes sense to everybody. Okay, not that I think it'll be a real difficult thing, but if it's giving you trouble, then come and ask. Okay. All right, so for number 1 here, right, we have nitrogen and iodine. So this is going to be nitrogen triiodide. Okay, and again, that's one that probably needs to be hyphenated. Okay. And then for this one here, we've got carbon and iodine. So this is going to be tetraiodide. How many of you have capital letters on any of these? We just got to make sure we're practicing not using the capital letters. All right. For number 3, I've got 2 nitrogens and 3 oxygens. This is going to be dinitrogen triiodide. Sorry, oxide. Get 2 iodines in a row. Trioxide. All right, and then for number 4, we've got tellurium and astatine. So this will be tellurium diastatide. Okay, questions on those 4? All right. Try the rest of them there. Okay, so for number 5 here, I've got 2 phosphorus, I've got 3 sulfur, so this is going to be diphosphorus trisulfide. And we've got 1 oxygen, 1 sulfur, so this is going to be oxygen monosulfide. Okay, how many people have done 7 and 8? Okay, let's look at those 2. All right, we got 3 silicone and we got 4 phosphorus, so we have trisilicone, okay, tetraphosphide. Okay, and then for number 8, we have sulfur and 2 chlorines, so this will be sulfur dichloride. Okay, questions on any of those so far? How many people have done the last 2? Okay. All right, so we have silicone and we have hydrogen. Okay, in this case, how do I know that this is not an ionic compound? Right, hydrogen's second, right? And anytime hydrogen is listed second, it's behaving as a non-metal because it can behave as both. Okay, so we have silicone tetrahydride. And lastly, we have 4 borons, then we have 3 carbons, so we have tetraboron tricarbide. It's probably not even a real compound, but okay, sometimes we just put things together to practice our naming, whether they actually exist or not. Alrighty. There were a couple other ones here, but I think we get what we're doing here. So, all right. Here's the trick. It's easy when you know they're all molecular, or you know they're all ionic, or you know they all need a Roman numeral. Okay. The challenge is, can I tell when I have to apply those rules? Okay. So this one is a mix of a number of basically everything we've talked about. Some of them are ionic. Some of them are ionic and need a Roman numeral because they have a multivalent metal. Some of them have a polyatomic ion. Okay. Some of them are just molecular. So I want you guys to try those ones, see if you apply all the right rules. When we're doing this, the first step is identify is it ionic or is it molecular, okay? And then apply the proper rules after that. Okay, give you a few minutes on that one. Okay, so number 1, ionic or molecular? It's ionic. Lithium is a metal, okay? So we name it as such. This is simply lithium chloride. Excuse me. All right, for number 2, ionic or molecular? It's ionic. Chromium is a metal. Okay. Does chromium have more than one possible charge? It does. Okay, so this one's also going to need a Roman numeral. Which Roman numeral is it going to need? Yeah, it's going to need a 3. Okay, because fluorine is a -1, and there's 3 of them, so there's only 1 chromium. So at chromium 3 fluoride. Okay, and then number 3, ionic or molecular? It's molecular. Okay, so this stuff is going to be phosphorus tribromide. Okay, and number 4, ionic or molecular? Okay, does it need Roman numeral? It does not. Okay, this is just zinc iodide. All right, seems like we get it. Keep going, guys. Here. All right, so for number 5, ionic or molecular? It's molecular. Silicone is a nonmetal. All right, so we have silicone dioxide. All right, and number 6, ionic or molecular? Molecular. Okay, so we have carbon tetrasulfide. Okay, and for number 7, ionic or molecular? It's ionic. Technetium is a metal. It does not exist in nature, actually. It is man-made, which is why it appears different on most periodic tables. Okay, TC is number 43. You can see here that on my periodic table, it's a hollow outline. Okay, that means synthesized. All right, so we have, then this will be technetium iodide. Okay, again, the 7 doesn't matter. It just happens that technetium has a 7+ charge. All right, number 8, ionic or molecular? It's ionic, okay, and it has a polyatomic ion in it. So this stuff is going to be sodium hydroxide. And we did that one as an example. But okay, keep going. I'll let you get ahead of me again. Okay, so for number 9, ionic or molecular? It's ionic. Calcium is a metal. All right, and what's SO4? Sulfates. Okay, and this one didn't need the brackets, but brackets are around it. Okay, if you're not putting another number beside the polyatomic ion, you don't need brackets. Okay, all right, number 10, we have ionic or molecular? It's ionic. Okay, K stands for potassium, and what is MnO4? Permanganates. Yeah, this stuff is pretty funky stuff, actually. Potassium permanganate. is actually little purple crystals. Yeah, they used to use it. They used to make a solution of it and use it as a fungicide. It would kill like athlete's foot and things like that. People would soak their feet in it for a little while. The only problem with it is that when in solution, it causes a chemical reaction that stains your skin. Okay, and if you have really light colored skin, okay, your skin will turn quite dark brown. Okay, I had a kid when I was first starting teaching, so like before you were born, and we were doing a lab. This kid never listened. It was like the bane of my existence. And a bunch of times before the lab, I said, guys, make sure that when you're using the potassium permanganate, you don't pick it up with your fingers, because if you do, you'll stain your fingers really, really dark brown. Okay, like people will look at your fingers and go, where? Yeah. Okay. And so anyway, a little while later, he comes over to me with the sample tray. He's going like this. And he's playing with the crystals. He's like, Coder, these are so cool. And I'm like, yes, they are. Do you remember what I said about them? No. Okay. And I just let him keep playing with them. By the end of class, I mean, because it's not going to hurt him. Right? It's nothing like chemically going to poison him or anything. Okay? Well, at the end of class, like, Coder, I got to go wash my hand. You go right ahead. You got sandpaper and bleach. That's the only way that's coming off. Like up to the first knuckle on his thumb and first 3 fingers was just dark brown. And he was pasty. So it was just so obvious. And yeah, it was like that for like 2 weeks. He listened a little better. Not a lot better. A little bit better after that. But yeah, it was, pretty gross. But funny. Karma. That's what that is. Okay, number 11. Okay, we have a molecular compound because nitrogen and oxygen are both nonmetals. So this will be nitrogen monoxide. All right, number 12. We have an ionic compound because we have a polyatomic ion, but we also start with a metal. Okay, this will be beryllium cyanide. Right. All right, how many people have done all of them? Up to 15. Okay, let's just go through them all then. All right, so for number 13, we've got barium with cyanide again. So it's an ionic compound. Okay, so we have barium cyanide. What's that? 14, yeah, nacho. Okay, it's close. It's close. All right, it's actually something that does go in a lot of foods, though. This is sodium hydrogen carbonate, which is also commonly known as baking soda. This is baking soda. Yeah. We also sometimes call it sodium bicarbonate. That's another name for hydrogen carbonate, is bicarbonate. So sodium hydrogen carbonate. Okay, and then for number 15, okay, this is a molecular compound. Okay, but it also looks like a polyatomic ion. Anybody notice there's a polyatomic ion with the same formula? Okay, so here's the thing, because this happens once in a while. Okay, if this isn't attached to something else, it's a compound, and we name it like a compound. This is phosphorus tetraoxide. If it was in a compound like, what's the charge on phosphate? 3? -3? Yeah. Okay, so if it was in a compound, it would look like this. Then we would say this is magnesium phosphate. Okay, so if it's not in a compound, we name it like its own compound. If it's in a compound, we name it like an ion. All right, everybody all right with that? Okay. Pardon me? Cyanide? Yes. Yeah. The cyanide ion interrupts the metabolism of the cell. Essentially, it doesn't matter that you're still breathing. Your cells cannot metabolize oxygen and sugar together. And so that reaction stalls and you just get really tired. And yeah, it's usually, people used to use it as a poison, like, back in the dark ages when they're trying to assassinate someone, they put cyanide in, but it has a distinctive taste. And so if it's in your food in a large enough, it tastes kind of like a bitter almonds kind of a taste. So if ever you're drinking something and it tastes like bitter almond, stop drinking. Not that anyone's going to try to poison you, but yeah, okay. It does have a bitter almond kind of taste to it if it's in strong enough concentration to hurt you. Okay, questions on any of those? All right, so we'll probably work a little bit on that a bit today, but first we're going to talk about writing the formulas now. So going the other way, we've been looking at here's the formula, write the name. Okay, now we're going to look at here's the name, write the formula. But that's the kind of stuff that's going to be on your quiz tomorrow, which I will post after school today. Okay, so it'll be on Google Classroom, okay, and posted after school today. All right, so now going the other way, okay, if I'm given the name and I have to now write the formula. Again, the rules are different for ionic versus molecular compounds. Okay, ionic compounds, you got to do the drop and swap. Okay, which is pretty easy, right? You just take the numbers. Okay, there's only a couple of exceptions when the drop and swap happens that you have to fix. Okay, the first thing is if you're given the name of a compound, you want to decide whether it's ionic or molecular. So let's say I got this name here. Okay, so I've got magnesium iodide, so it's ionic. The next step is to write out the formulas for both of the things involved. So magnesium is Mg, and I want to write its charge. What's the charge on magnesium? +2. All right, then I'm going to write the next one, iodine, and it has a charge of -1. Okay, at this point now, I can drop and swap, so balance the charges. So I bring the 2 and I put it down here, and I bring the 1, we don't write ones. I've got my formula finished. Okay, fairly straightforward. Only exception happens if I was to get, instead of magnesium iodide, if I got magnesium oxide. Okay, then I would have Mg, 2+, and oxygen, 2-. Okay, I don't write it like this. Okay, they cancel each other off. So the general rule is it's like fractions. If you can reduce it, reduce it. Okay, if you got 3 and 6, you reduce it down to 1 and 3. 1 and 2, 1 and 2. Wow. What a brain fart that was. Okay, yeah, so you get the idea here. If you can reduce, reduce down to the lowest terms on ionic compounds. Because sometimes you'll get a molecular compound where you get like a 2 and a 4, but you have to leave it that way. Okay, because that's what the prefixes tell you it is. All right. Now, a couple of other exceptions. We talked about this a couple of minutes ago. If I have, let's say, this one. Okay. If I have beryllium nitrate, okay, I still do the same things. I'm going to go Be, and it's a 2+, and then I'm going to write nitrate, which is a polyatomic ion, and it's a -1. Right? When I drop and swap, the 1 will come here, and the 2 will go here, but I need to enclose that in brackets so it isn't NO32, and it's NO3 bracket 2. Okay, so the drop and swap still applies to polyatomic ions, but sometimes you'll need to enclose them in brackets. Okay. All right, what would this one be? Try this one. All right, so for this one here, where's ammonium? It's in the table of polyatomic ions. It's the only one that's positively charged on your table. Okay, so ammonium is a +1, and sulfide is a -2. So when we drop and swap, the 1 goes here, and the 2 comes here. Okay, so we would have NH42S. Okay, everybody all right with that? All right, one more thing here. All right, so I've got this one. It's ionic, but it has a Roman numeral in it. What does the Roman numeral tell me? It doesn't tell me there's 2 copper. It tells me that the copper's charge is 2. Okay, and that's a very common misconception. Okay, you wouldn't believe how often I see people just put a 2 beside it because there's a Roman numeral 2 there. Okay, so copper is Cu, but it can be a 1 or a 2, but the Roman numeral told us that this is the copper with the 2 plus charge. Okay, and it is with sulfate, which is a -2. So those work. They cancel each other out. CuSO4 is our formula. Okay, everybody all right with that one? Okay. For molecular compounds, super easy. You read the compound's name, you write the formulas, and you use the prefixes to tell you the numbers. Okay, so if it's diphosphorus, if it's carbon disulfide, okay, then I know there's 1 carbon and there's 2 sulfurs, and I just write it that way. If it's tetraphosphorus decaoxide, tetra means 4, so there's 4 phosphorus, deca means 10, there's 10 oxygens. You don't have to worry about dropping and swapping or doing anything else. You just use the prefixes to get the numbers. All right, and as we said, in molecular compounds, we don't reduce, because I could reduce this if I wanted to, right? I could take it down, okay, divide both of them by 2 and get 2 and 5, right? But I'm not going to do that because it's molecular and I was told what the numbers were. If I had an ionic compound that came out to 4 and 10, then I would reduce. Okay. All right, so in your chemistry workbook package, right? So if we open that up, right after the atom questions, you'll see a bunch of worksheets on naming. We're not probably going to do all of them, okay? But we're going to start and just practice some of that here today. See, that was working yesterday. Okay, so they start on page 2, like I said, right after the atom questions you did the other day. Okay, and you have some here where you need to write the names, okay, of these compounds. Now, what I'm going to do is I'm going to post the key for this on Google Classroom. So as you go, it's probably not a bad idea to check the key so that you know if you're doing it right. Okay, I would say don't do more than about 4 or 5 without checking. Because the worst thing you can do is do a whole page, then check and realize you've practiced doing something wrong like 35 times. Okay? Practice makes permanent, not perfect. Okay? If you practice something wrong, you're only going to get better at doing it wrong. All right? So we don't want to do that. I'll put the keys on Google Classroom here right away, and then they'll be in the stream. You can just click on them, match up whichever one you're working on, and check them back and forth. Absolutely.